Okay, let's talk about, we'll just give it the easy title of vertical circular motion. And we're almost out of time, so I'll do this really fast. Um, so let's say you want to ride a motorcycle through a loop. And you're wondering, essentially, like, how fast do I go such that I don't fall off of the loop, right? Um, so what are you going to have to take into consideration? Well, you know that if we just look at the horizontal kind of equivalent of this, riding around and around and around like this, or actually just swinging something around, let's say this is a puck on a frictionless table and we're looking down from above, we have a centripetal force like towards the center, right? So in other words, when I go around this loop, at all times, I'm going to have some kind of centripetal force pushing me towards the center, okay? The key is, if I get to the top and I'm going too slow, gravity is providing the centripetal force, right? But if that centripetal force is too great for the loop that I'm on, I'll fall off the loop, right? So what we can say is then, before we get to the point of solving a problem like that, let's just think about if I take a cork on a string and I whip it around in a vertical loop. So here's my arm, here's me standing here, my arm attaches directly to my neck. I'm so jacked. Just super, super beefy guy here. But I'm like whipping this around in a vertical circle, okay? If I were to test the forces on here, I would find an oscillation of forces. There would be a larger amount of force at the bottom than there is at the top if I were to attach a little force sensor in here, okay? That would not be the case in the horizontal scenario. In the horizontal scenario, at a constant velocity, force would stay constant. Why would I find an oscillation of forces? Good. That is the key. We have a gravity that is working on this at all times, and I'm just going to kind of make it look funny, but whatever, okay? And no matter where I am around this circle, gravity is always pointing down. So what that means is, here, the tension in this rope has to apply Fc to make it go in a circle, plus it also has to supply Fg. And I know this is true because if I were just standing there, holding a rope with a cork on it, this would have an upward force equal and opposite to Fd. So the tension in here would be equal and opposite to Fg, right? Just when I'm sitting there. That never goes away when I'm at the bottom, okay? And then up at the top, it's slightly different. Well, now, I actually can subtract the value of Fg. Now, I'm just going to put absolute value here so we don't get confused, okay? So what is essentially happening is gravity is supplying some of the centripetal force in the vertical direction. Does that make sense? So think of a projectile, right? If I like throw a projectile, okay, you could almost think of it in a way as a bit of centripetal motion or circular motion. And gravity is supplying the centripetal force sort of towards the center. Now, I know that's not how we think about it, right? But right at the top here, if you go at just the right speed, tension could technically drop to zero. And all of the turning force, all the centripetal force, could be supplied just by gravity, right? So we can do this. We can just either add or subtract whatever value g is. But we want to know about the motorcycle. So we want to know what happens, and I'm rushing a bit, when all Fc is supplied by gravity. So that's what we're going to just take a quick look at here. A motorcyclist going around a loop. This should be a perfectly circular loop. We'll talk later as to why things like roller coaster loops are not usually perfect circles. They're like, what do you call that shape? Ellipses? Yeah, kind of like an ellipse, and there's a good reason for that, and it has to do with what happens to radius at the top of an ellipse. I'll give you a hint, it gets smaller. Okay, but whatever. So what we want to know is, well, at the top, we want all centripetal force to be supplied by gravity. So this is the premise we work on. Fc is supplied completely by gravity. So if Fc equals Fg, let's see what those things actually are when we open them up. This is mv squared over r. And so that is equal to mg. I think you can see where we're going with this. Mass becomes irrelevant. Okay? And what we're interested in is what is the minimum velocity that I can rip through this loop at and have gravity provide all of the centripetal force, okay? And that is called the critical velocity. So this is the critical velocity for a vertical loop. Okay? Now, this also has other applications. Like, for instance, let's say we're up above the surface of Earth and we're a satellite. Well, basically, what's going on here is we're going just the right velocity such that all of our centripetal force is provided by gravity. So you can actually use a formula like this, or circular motion formulas, to sort of predict the motion of objects in orbit, which can be very, very handy. Okay. Now, in reality, we're doing some approximations because orbits are usually a little bit elliptical. But they're close enough to circular that these, for the most part, will work, right? If you actually went to work at like NASA or something, the mathematics would probably be a little more in depth. But this is a nice approximation, and it works very well for lots of problems. So I'm going to leave you with a little bit of a practice here. We'll say what minimum velocity is necessary to just make it through a 10-meter tall, be careful here, 10-meter tall vertical loop. Okay, so that's your homework challenge. And by the way, why do I say minimum velocity? What if I go through here at faster than what I calculate for the critical velocity? What happens then? Right, I'll be fine. In fact, what will happen is this will start to provide a normal force on me, right, to keep me following the path. So faster is fine, slower is bad.